this formula that I sort of derived over here, but you know, understand more of the concepts, why blah blah blah. There's some other more advanced work that would have to go into it. You write the incident wave as an electromagnetic wave, and the refracted wave, and the transmitted or refracted waves, and then you meet some boundary conditions, the surface, and continuities of some of the components of the electric field, and so and discontinuities, and so it's beyond the level of this course. But let me just roughly tell you what this Brewster's angle is about. Okay? All right, so let's consider the following. So let's say that this is a surface that separates this medium, air in this case, with some other medium, whatever. Let's say this is a medium that light can go into. Water, glass, something that light can, obviously light doesn't go into the table. It is opaque to light in the visible region of the spectrum. But let's just say that this represents the boundary. Right? And if I shine a beam of light, let's say like this, like if I didn't bring my laser pointer, it's in my office, but if I shine a beam of light like this, remember that I said that, well, that would be the normal to the surface. And if the incident light comes in like this, the incident beam and the normal define a plane. And the reflected ray and the refracted ray they have to be in the same plane. It's called in that plane of incidence. So you can imagine, if you like, there's a plane, right? And so the reflected ray is going to be in this plane, and the transmitted ray is also going to be in that plane. If I put it like this, well, anyway, there's this plane of incidence, right? All right. Now, if the wave travels like this wave consists of an electric and magnetic fields that are oscillating, right? Both the electric and the magnetic fields oscillate in directions that are perpendicular to this direction that the wave travels. This is just from the pointing vector, right? The pointing vector says that the direction in which the wave travels is in the same direction as this cross product. So the direction in which the wave travels is in the direction of the cross product of the electric and magnetic fields. But for any cross product in the world, I don't care, right? If this 1 mu naught is a positive quantity, this vector, right, is in the direction of E cross B. And in general, this vector has to be perpendicular to E and to B. Right? When you take the cross product of two vectors, the third vector that you get is perpendicular to both vectors that you're multiplying. Right? It has to be perpendicular. So if the wave travels this way, that means that the electric field has to be perpendicular to this. Electric field has to be perpendicular to this. So maybe the electric field is like that. That's perpendicular to the ruler. Or maybe it's at an angle like this. Well, not to the ruler. To the ruler, all of these directions are perpendicular. Maybe it's better if I do it like this. Here's the wave coming in, and the electric field can be in any plane that's perpendicular to this marker. Yes. So suppose the wave comes in like this. You have this plane of incidence, right? And then what if this electric field is pointing this way? Let's say the plane of incidence is the board. So that's the plane of incidence. So, instead of, and then this is the boundary over here, so that's the normal. So the normal is like that. I shoot a beam of, and this is the boundary. medium 1, medium 2. I'm sort of like bringing this to here, so that's the normal, right? And I'm drawing the light wave coming in like this. So the electric field has to be perpendicular to that line. Correct? So the electric field could be oscillating like this. That's perpendicular to that. The electric field could be oscillating into and out of the pore. That's also perpendicular to this red line. But the electric field doesn't have to be like this or like that. It could also be at an angle like this. That's still perpendicular to this, right? So it's like if I draw something like that, this is perpendicular to the ruler. This is perpendicular to the ruler. This is perpendicular to the ruler. Perpendicular, if I stay in that plane, that's perpendicular to the ruler. So if the electric field is at some angle over here, like this, right? That's perpendicular to the direction that the wave travels. I can resolve this electric field into a component that points this way. And another component that's perpendicular to the plane of incidence, which would be out. Let me say out is like a dot. Right? So the board is the plane of incidence. So if I have a vector like that, some vectors, if I have a vector like that, I can resolve that into, well, here's the, if I have a vector like that, I can resolve this into a component that's parallel to the plane of the board and another component that's perpendicular to the plane of the board. That way, these two components of the electric field, right, can be used to replace the original electric field vector, which is the sum of those two, like that. Get it? In general. And so this component of the electric field is oscillating that way, this way, that way, this way, that way, this way. This other one is oscillating out, into, out, into, out, into. And so Brewster, if the angle of incidence is of a particular value, which is known as Brewster's angle, I guess you can call it B, if that angle is a special angle, then what happens is the following. First of all, the light comes in like this, right? It comes in like this. There's going to be a reflection, and that reflection is just the angle of reflection is equal to the angle of incidence. So this will be the same angle as that. This is the reflected ray. And then the refracted ray is going to go like that. And now the angle of refraction is this. Let's call it theta 2, and this was theta 1, which is the same as this, right? Now, if this angle is a particular angle that only depends on the indices of refractions of the two media, then this electric field that's, let's say, parallel to the surface, and the other electric field that's in, out, I'll just say E perpendicular to the surface, right? Then this, the wave comes in like this, and if it comes in at the right angle, I don't want to say right because you might think that that's 90 degrees, at the correct angle or a particular angle, then of these two components, so imagine they're oscillating, so they come in like this, and then of these two components, only the component of the electric field that's parallel to the surface, or another way of saying it, perpendicular to the plane of incidence, will be reflected. So over here, you're going to have just that. Only that component is going to be reflected. The light that goes through, some of the energy is going to be oscillating in and out, but you're also going to have, oscillations like this. But the reflected ray will only have an electric field component that's perpendicular to the plane of incidence. And what Brewster discovered, this is somebody's last name, is that whenever this effect happens, the sum of the angles between the angle between the reflected ray and the refracted ray is 90 degrees. But if this angle is if the angle between this and this is 90 degrees, well, what's the angle between this and this? 180. So what must be this angle added to this angle?
90 degrees.
90 degrees, right? So therefore, theta 1 plus theta 2 has to be 90 degrees. I'm calling theta 1 Brewster's angle. So that means that theta 2 is equal to 90 degrees minus theta Brewster. And if I apply Snell's law, if I say N1 sine of theta 1 equals N2 sine of theta 2, then I can do this. N1 sine of theta 1, I'm calling it Brewster's angle. And that's N2, the index of refraction of the medium where the light will be transmitted into, multiplied by the sine of theta 2. But theta 2, I can write it as 90 minus theta b. And then I can use one of those trig identities. This would be the sine of 90 cosine of theta b minus the sine of theta b cosine of 90 degrees. But the cosine of 90 degrees is 0, and the sine of 90 degrees is 1. So therefore, I have that N1 sine of the Brewster's angle is equal to N2 times the cosine of the Brewster's angle. And then I can say that I can divide by cosine of the Brewster's angle, so I have that the sine of the Brewster's angle divided by the cosine of the Brewster's angle is equal to N2 over N1. The index of refraction where the light is transmitted into divided by the index of refraction of the medium where the light was coming from. And so therefore this is, you can combine these two into the tangent of Brewster's angle. So if you have light that is, for example, randomly polarized, or it's linearly polarized in some direction, and you want to change the direction of that polarization, and you want the polarization of the light to just be perpendicular to this plane of incidence, just shoot it at some surface, ensure that the angle of incidence is equal to this, so that the tangent of that angle is the index of refraction of this medium divided by the index of refraction of the other medium. If you wanted to solve for the angle, it's just the arctangent of the index of refraction of the medium where the light is transmitted into divided by the index of refraction of the medium where the light was incident from. And then you can get that angle, then shoot the light this way, and when you can be then certain that when the light reflects, this light that reflects is going to be polarized with the electric field only oscillating along this direction that's perpendicular to the plane of incidence. Or said differently, it would be polarized parallel to the surface, to the boundary between the two media. So that's one way of polarizing light, right? By letting it reflect from a surface, and then you just ensure that the angle of incidence is equal to this angle, such that the tangent of that angle is equal to the index of refraction of this medium divided by the index of refraction of that other medium. So it's interesting if you want to know what is the formula for the Brewster's angle, it's the tangent, and this is the index of refraction of the medium where the light is transmitted into divided by the index of refraction where the light was incident from. If you want the critical angle for total internal reflection, right, it would be the index of refraction of the medium where the light is transmitted into divided by the index of refraction where the light came from. So one of them has a tangent trig function, the other one has a sine trig function. some laser cavities, one can use prisms, and the light, you have a prism like this, and the light comes in like, this is the direction of travel of the light, and if the light is polarized in various directions, it hits the prism, right? And you ensure that it hits at the Brewster's angle, right? And then it'll reflect, right? And that'll be, for sure, that'll be polarized in a direction along this, face of the prism. And but anyway, they're used. It's something that's used in one application is in laser systems. Okay. So maybe you can read about it. I mean, it's just a formula. You plug it in, and but there's more to it, but we don't have time for that. And so a little bit more. So the next topic is chapter 34. And here we talk about